Okay, good morning, everybody. Today, we're going to continue with our lab session from last time on Model Predictive Control. So this was the script we were working with. It's called X2, and it's in the folder Optimal Control Casadi Adam. So you can open it if you haven't already. And what we were doing last time is basically implementing the code that goes inside the MPC loop. And that code consisted mainly in these like 20 lines. So we have, first of all, the warm start, where we take the last solution computed at the previous iteration of the loop. And then we set the current state of the system as the initial state of the optimal control problem. We call the solve method. We have to call this inside a try except block, because in case the solver raises an exception because it was not able to solve the problem, at least the script doesn't stop. And we can still retrieve the solutions that the solver has computed, even if it's not really a correct solution, by taking this opti.debug object and setting it equal to solve. Then from the solution of the optimal control problem, we recover the joint torques, and we send the joint torques to the simulator. We have three options for the simulator. Ideal is basically just using the prediction of the optimal control problem as the next state. So that would be an ideal situation. That's why it's called ideal. Pinocchio instead is a standard multi-body dynamics library, which takes the torques and computes the accelerations and integrates them. And Mujoku is instead a more complete and complex simulator where we can also introduce obstacles and simulate collisions with the environment, but we are not going to do that because you don't have it installed. And then we have a couple of prints to check whether we are violating the joint position limits. Yeah.
I couldn't attend the lecture on Monday, and the recording was blank in the second part where you did this. Could you shoot to Git so that we can download?
No, but you can find the solution in the file joint space MPC, which is in the same folder. This is supposed to remain empty because it's the template. I did this on Monday, but I'm not pushing it on GitHub because on GitHub it has to remain empty because that's the template for next year students. So okay, so you're saying that the part where I implement this is not in the YouTube video. Okay.
All with Jupyter Notebook that existed, but once that was done, it was not. I think it was after the break. The second half was just.
Okay, I'm gonna check that later. I hope I didn't stop recording because in that case, of course, I cannot recover it. I hope it's just a mistake I made when I uploaded the video because that's recoverable. No problem. So we stopped at this point, and the result of running this was not great. So if I do Python x2.py, okay, my browser took too long to open, so we didn't see what the robots really did. Let's try it again. Okay, so it doesn't work. The robot is supposed to reach this configuration with the arm in the upward direction and stops there, and instead it goes nuts. And we can see also a lot of error prints in the terminal showing that we are violating joint position limits all the time. The only positive note is that computation time is pretty good, except for the very first loop, which takes twice as much as the others. After that, we are always roughly at 15 milliseconds. It's not bad. So any idea why this may not be working? Because I left you with this question. Try to think why it's not working.
Is there Pinocchio as the simulator?
Good question. Yeah, I think so. Yeah.
Okay. So,
if we set ideal, probably it's gonna work. Yeah, roughly it works. This works much better than with the other case, but ideal is not a real simulator. It's just an easy setup to test the code. The real simulator is Pinocchio, so we should make it work with Pinocchio.
We check the starting position of each loop.
The starting position of?
I mean, can you go on the code while you set the starting position? I mean, the x0 of the problem.
The x0 of the problem is the same, is the state of the simulator, basically. Because after we simulate, we set x equal to basically the robot state in the simulator. And this is the value that is used here for setting the initial state. So
is the correct value of the approximation?
Sorry, go again.
I mean, is the correct value not I mean, it's the value where the robot is or not?
It's the real state of the robot. We are not using the prediction as initial state. Yeah. That I think would make it worse. So everything that I've implemented is correct. I didn't make any mistake on purpose. So the code there is correct. So the reason why it doesn't work is not related to an implementation mistake. It's just a conceptual thing.
Are you considering the final cost function? Because
Let's check.
Because it's the weight and the root final. I think it's set to 0. And if we are considering a finite horizon, I mean, the error accumulates because our model and the Pinocchio model are different. So,
I mean, our model is not uncertain or imperfect. We are using the perfect model of the robot. So the simulator and the controller now are using exactly the same model. It's just that the controller is not converging. So the optimization solver of the controller is not converging. And so the solutions that we get are not exact because we only do 3 iterations.
So it will be the cost function.
What do you mean?
On the same code, I have the final weight set to 0.
Yeah.
So basically, the cost function is not considered.
I mean, we are only considering the running cost.
Okay.
We don't have a final cost, but we have a cost.
Yeah, but final cost would help.
Final cost could help. Yeah. So what do we do?
We increase the weight of the final cost.
Okay. How much? 1.
I don't know.
1 is huge, but we can do it. Let's see. Much better. Let me check. Yeah, it's still Pinocchio. White works better with a final cost. Well, everybody can answer, but I mean, since you were the one suggesting it.
It's we are considering a finite horizon, so it's the thing we said that the last time. So if we consider the finite horizon, we have to compensate in some way the fact that we don't have an infinite horizon, so we put a finite constraint that a finite cost that simulate the infinite horizon. So the function recursively converges. So
yeah, that's roughly it. We should differentiate though between final cost and final constraint. So here we are working now with a final cost. However, we could also work with a final constraint. They are both useful for like compensating for the lack of an infinite horizon. So shall we try also with a final constraint? So we set this back to 0. And here where I create the problem, I can add a terminal constraint. So opti.subject to x minus 1. So that in that way I take the last state of the horizon. And what should be the terminal constraint?
On the position, I mean, the state of the robot, the joint position are in the desired joint position. So the norm of the error is
We could try. Maybe it works.
I mean, it's a aggressive solution.
It's a bit aggressive, I agree. Okay, so I'm saying that the final joint positions should be equal to the desired joint positions. Let's see if it works. I have never tried. No. Infeasible problem detected. You're starting here, you have an horizon of like 60 milliseconds, and you're saying that at the end of the horizon, you should be there. Is that feasible? No. So that's not the terminal cost, the terminal constraint that we need. What did we say about the terminal constraint set? What's the property that we want this set to have? You're not studying, guys. Can look at the notes.
Should be in the control invariant set.
It should be a control invariant set. What is an example I gave you of a control invariant set? Zero velocity set. So what should be the terminal constraint?
The velocity of the joint.
Exactly. Yeah, we should set the velocity of the joints equal to 0. So if you do so, we have a control invariant set as terminal constraint set. And this ensures what? Recursive feasibility of the problem. So if the problem is feasible at time step 0, it's going to remain feasible forever. Let's see if that works. It does work. And actually, the effect is quite similar to the terminal costs that we added before. Can you guess why the effect is similar?
In the cost and penalizing high velocity. So I want to minimize velocity. So I can be easy.
Yeah, I mean, you can see this terminal cost here as a relaxed version of this terminal constraint. They're very similar. This one, of course, is a hard constraint, so you want the velocities to be really zero, not 10 to the minus 3 or 10 to the minus 4. They need to be 0, period. With this one, you're not going to get 0 terminal velocities, but you're going to get pretty small terminal velocities. And that's going to be good enough in this case.
Even just why we should choose the constraint. I mean, I'm ensuring feasibility, but maybe with just the cost. I mean, I could resolve the problem like with, as you said, small velocities. And maybe I'm just enlarging my possibility of a solution, even if it's not perfect.
Yeah, I agree. The only advantage of the terminal constraints is that you don't have any weight to tune, so there is no room for errors, basically. You implement this and you're done. There is nothing else to do. If you go for the terminal cost, you need to decide how high this weight should be. Because, well, if it's very high, then it's going to be the same as having a terminal constraint, basically. If it's too high, it could even lead to numerical issues in the solver. So it could deteriorate the quality of the solutions that the solver finds. And if it's too low, then you're going to have constraint violations as we had before. And so it's a bit harder for the user because you have to tune the weight. But I agree that actually it may lead to a better performance because these terminal constraints, as we said, it's very conservative. We could also see the motion of the robot. It's quite slow because it needs to be able to stop in 6 time steps, which is the horizon is currently using. And so it can never reach high velocities. So we could also print that. So every time we simulate, then what we can do is that we could say print max val np.max of x and q. So we are printing what the maximum velocity is. Maybe I can print it directly above when I'm doing the other print. What did I do? I forgot parentheses here. So the maximum velocity is a bit hard to read this way. Let me redo it. So it's a bit easier to read. The maximum velocity is reached roughly here, and that's 0.3. Oh no, we have way higher velocities here, which is 6. We can check whether by using the terminal cost instead of the terminal constraint, we can reach higher velocities. So let's remember this number, 6. So I'm going to remove now the terminal constraint, and I'm going to reintroduce the terminal cost. Let's see what are the velocities. Well, even just by looking at it, it looks faster, right? The motion. But if you look only at the peak velocity, it's not higher. Well, rough is it's not higher by a lot, because here we were 6.03, now we are 6.08, but that's not really significant. So maybe we should look more at how much time it takes to reach the target. Maybe that's more significant. So let's think a moment. I need to, my target is in joint space, so it should be quite easy. I can simply compute the error and check when the error is below a threshold. I print something. Let me do it here. Reach flag equal to false, and this we're gonna move it outside. And then here I need to check the reach error, which is the norm of Q minus Q dash, which is called Q dash, exactly Q dash. If reach error below, I don't know, 1 millimeter, well, it's in radians, it's not in meters, sorry. So we can put it even a bit, maybe 10 to the minus 2, which is like half a degree. Then we print target reached at time step I. And then we say reach flag equal to true. And here we also add this condition so that we don't keep printing this over and over. That's it. So this is with the terminal cost. We reach the target at time step 46. Now we try with the terminal constraint. We reach the target at time step 70. So it takes significantly longer to reach the target. We couldn't see the difference in terms of peak velocity, but we could see it in terms of how much time it takes to reach the target, which is actually the most important aspect. So you can see that, yeah, with the terminal constraint is easier to work with, and it gives us immediate guarantees of feasibility. But we have this downside of making the motion much more conservative. Yeah.
And if you try to decrease the weight of the punch cost,
We can do that. It's a good idea. So before we were reaching at time step 46. Instead of 1, we could set it to 0.1. Hopefully we're gonna reach it even faster. So instead of 46, let's see. We had a bit of an overshoot. And so actually, no, it didn't improve. That's too low. And you can see we have this problem of needing to tune this. And the tuning is going to depend on the target and on the initial state. So it's a bit annoying to do this tuning. Yeah, you had a question?
Did you reduce the weight of the final cost? But what happens then? Why does it make it improve?
Well, we just tested it. We reduced the weight from 1 to 0.1. We were expecting an improvement in terms of reaching the target faster, but actually that didn't happen. We had constraint violations, and we actually ended up reaching the target later.
Why did it make it faster?
It should make it faster because if you penalize less the terminal velocities, then the solver is basically able to plan a trajectory that reaches higher velocities, and so it should reach the target faster. We can probably see it in the other way. If we increase the terminal cost, so instead of 1, we set it to 10. Now I expect this to make it go slower. So instead of 46, it should reach the target in more time. We can see visually that the motion is slower. And instead of 46, now it took 68 steps. So it's not as slow as the terminal constraint, but it's very close to it. So at a certain point, if you keep increasing this, it's gonna converge to the same result of having the terminal constraint, basically. But there is a sweet spot where you can get a bit of a better performance than with the terminal constraint without having constraint violations. But that sweet spot is not easy to find. And the only way you have to find it is by trial and error. So if you want to be sure that you have safety, so recursive feasibility, terminal constraint is the best option.
Here the spot is setting the final cost to 1.
Yeah, it seems that your colleague has found the sweet spot at the first guess. Very good intuition.
But isn't it like always smarter to do a final constraint instead of a final weight? Because like if I have a final constraint, I'm 100% sure that it's reached and the constraint is not violated at all. Whereas if you have the weight, it just minimizes the costs. And there could be a violation that you don't even know if there is or not. Because it's just like an optimization problem at that point anymore, and not a constraint.
Yeah, exactly. That's why I said, I mean, if you want to be sure that it works, you should use the terminal constraint. But if that results in a decrease of performance that's not tolerable for your application because it makes the robot move too slowly, then as a second option, you could try with a terminal cost, which is like a soft version of the terminal constraint, knowing that you're losing all the guarantees and you need to tune this weight so that it works. And the tuning, I mean, what we're doing right now is not at all sufficient to say that this is the right value for the terminal cost, because we are just testing one initial condition and one desired joint configuration. We should test it in a much more broad set of initial conditions and desired configurations.
And just for like understanding completely, our terminal constraint now is that we want to be in the control-invariant set.
Yeah, which is just 0 velocities.
How do we get to that 0 velocity constraint? Like, I get the idea of the control invariant set, but how do we know that it's zero velocity?
So there exists infinitely many control invariant sets in general for any given system.
Yeah, that was the one you like.
This is the only one that's easy, so that you get like for free without doing any offline pre-computation. And the reason why it is control invariant is because we are assuming that the robot has sufficient joint torques to compensate for gravity. And I mean, that's the case for almost all robot manipulators. And if that's the case, if you are in a configuration, whatever, with zero velocities, you can remain in that configuration forever. So you're control invariant because you can remain inside the set.
So that's basically like the one we are always using. We can just expect the robot to stay in that once we are in the result, because we get the torques are high enough.
Yeah. Yeah. And of course, there are other sets which are bigger that are control invariants, but those are not trivial to compute. So we will need to do some pre-computation, as I described. Yeah, we will need basically an algorithm for computing an estimate of such a control invariant set. And then we could use this estimate, typically represented with a neural network or with some like function approximation method, whatever. And then we could use this as a terminal constraint inside the MPC problem, but that's much more advanced.
That's for me to understand. If I have a control invariant set, but it just means that it's like stable and like I'm staying inside that set. Yeah, it could be like oscillating as well, as long as my oscillation is not unstable, right?
Yeah, control invariant sets, it's a bit different. I see why you tend to correlate it with stability. It's not really stability. Stability has a different definition, but they are somehow similar ideas. Control invariant set is basically that's a set that you can remain inside forever. Once you're inside the set, you can remain inside forever. It doesn't mean that you need to remain at a fixed state.
Yes.
You can keep moving. Maybe a limit cycle is a control invariant set because you're cycling always over the same sequence of states. Like if you think of like a humanoid robot walking,
yes,
the set of states, if it's a cyclic walking, the set of states that the robot goes through, that defines a control invariant set, basically. But none of that state has zero velocities. So zero velocity is just the easiest example, but it doesn't need to be a zero velocity to be control invariant.
Okay.
Okay. Thanks to you.
You said that we can use the algorithm, the
backward reachable set, yeah.
I mean, we can find such complex sets like the working set with such algorithm.
No, the example I just made, no, because that's not a backward reachable set. That's not a backward reachable set. You could find very easily a limit cycle and use that as a control invariant set. How can you find a limit cycle with the tools I gave you already?
No, I was asking.
No, now you have to answer. I mean, what's a limit cycle? It's a cyclic trajectory for a system. So it's a trajectory that starts and ends on the same state. Yeah, I mean, whatever. I mean, just how do you discover a trajectory that starts and ends at the same state? Human?
I could do a Nyquist plot and then
a Nyquist plot. Oh no, we don't do that thing here. No, that's like classic control theory. That works only for linear systems.
You could also do nonlinear, couldn't you?
I've never heard of that. Nyquist plot for nonlinear systems. No, I mean with the tools that we are studying here in this class, it's very simple.
Yeah, start optimization. I set up a nonlinear problem where the final state must be as equal to the initial state. I mean, set the function to 1 maybe, and then I hope it finds something.
Yeah, you just set up a trajectory optimization problem, classic one like this, and you simply add a constraint that the terminal state should be equal to the initial state. That's it. The solution is going to be a cyclic trajectory. So it's a trajectory that you can cycle on forever. So that trajectory is a control invariant set. It's a very thin one because it's just a trajectory. So it's not actually an improvement probably over the one we are using here, which is just zero velocities. But if this cyclic trajectory is somehow close to the trajectory that your system should be following during the motion, then it's fine.
Yeah, I have any other notable control. I mean,
no.
That other than zero velocity.
Basically, you have these three classes: either equilibrium points, so zero velocities for a robot manipulator, or cyclic trajectories. And in that case, none of the states could be at zero velocity. Maybe they're all at non-zero velocities. Or you can find backward reachable sets of any control invariant set is also a control invariant set. So starting from one of the two first examples, you try to find the backward reachable set of those small sets, and you get bigger sets, which now they are not thin. Yeah, what happens is like they get inflated basically, but not uniformly. They get inflated according to the dynamics of the system.
So the classic one usually is maybe zero velocity.
Yeah, you typically would start with zero velocities and then inflate it using backward reachable sets. There are other methods that don't go through this procedure, but they are more advanced, so we don't cover them here. Okay. So let's see a couple more things on this example. What could be another way to make the controller work well without relying on terminal cost and terminal constraint?
Visualizer.
Yeah. So now I set the terminal cost to 0. The terminal constraint is being removed. We can simply try to increase the horizon. So now we have an horizon of 6, which is pretty short. We can try to make it, I don't know, 10. And that's good enough. No, sorry, not really. We have some constraint violations, so 10 is not enough. Let's try 15. You can see now that the motion looks slower, but it's just because the computation time is larger. And so the simulation that we are seeing is not in real time.
Have used the iteration for each step because now we have a longer horizon.
Can try that. So this was good enough. So with an horizon of 15, we don't have any constraint violation. We actually reach the target very quickly in only 40 time steps. The problem is that now computation time is roughly twice what it was before, which is not bad if you think about it, because we have made the horizon almost 3 times larger. We went from 6 to 15, and we only had an increase of computation time of a factor of 2. So that's very good. I would have expected a bit bigger. It's typically, you can expect an increase of computation time which is linear in the size of the horizon. So if you double the horizon, you should expect doubling of the computation time. And it's instead cubic in the size of the state and the size of the control inputs. So if you make the state twice as big, computation time should grow by a factor of 8. Same for the control inputs. That's because of the sparsity of the problem. The increase with respect to the horizon is only linear. In this case, it was even sublinear. So 15 works, but we are not inside our computational budget for the time. We can try to decrease the number of iterations of the solver. We set it to 2 instead of 3. Not great. Lots of constraint violations. So no, we need 3.
But I mean, we aim to stay under the VT time.
Yeah.
Also before we didn't stay under the VT.
I know. I know. It's very hard, since this is not really a solver thought for doing MPC, to stay under the time step. But yeah, you're right. Even before, when we were at 6, we were not below DT, but we were very close to it. We were at 15 instead of 10. So you can imagine that with a bit of optimization there, you can get to that.
What is maybe using a specific solver, the smallest DT that I can achieve?
Oh, people have achieved like 2 milliseconds on manipulators using a like customized, super optimized solver. 2 milliseconds, I think, is the fastest I've seen. Yeah. And that's for manipulators. For other kinds of systems, MPC has been run even faster. It all depends on the system you're working with. Here, since it's non-linear and it has a 12-dimensional state space, it's hard, I think, to go faster than that. But if you have like linear system, you can go faster. So yeah, the horizon was one option. Let's see if we can find some other options. So let's go back to the horizon of 6. So now we don't have terminal cost, we don't have terminal constraint. Just based on your intuition, what could we do that makes the controller work better? Playing with these weights here. So now we have a very high cost on the position, 0 cost on the velocities, and very small cost on the accelerations.
You could take down the position weight because we have a final constraint.
No, we don't have as a final constraint. I removed it.
But we can take away the position weight, or like make it smaller at least.
I think we can just make it smaller and see what happens.
We adjust the others. I mean, we just
Maybe we can also add a bit of velocity penalty.
But that would make it slower.
Let's see. Yeah, for sure, it's a bit slower, but maybe it's good.
But what is our goal? We're trying to make it faster.
We're trying to not violate the inequality constraint, so the joint position limits, and reach the target fast.
But if we don't want to violate the position limits, then like we would have to make a higher weight for the positions. Right?
No, because it is a weight on reaching the desired position is not the weight for the position bounds, the joint position bounds. Those are inequalities which don't have any weight. Okay, so those are defined here. When I say that my state should be bounded between lower and upper bounds. So this is not affected by the weights. It's just a constraint. So with the modifications I just did, so decreasing the position weight and adding some velocity weight, so penalizing a bit the velocities with the running cost and penalizing a bit less the position error in the running cost. I stopped having a problem with the constraint violation. However, I didn't reach the target because you see that I never got the print that the target was reached.
Cost.
We don't. I mean, the final cost is only on velocities. The constraints on the final joint configuration made the problem unfeasible. So that we cannot have it, because since the horizon is short and we start far from the target, we cannot reach the targets within the horizon. Or were you talking about the constraints on the velocities?
Just said that we're zero, but like we first want to reach the target and then we consider how fast we are reaching it, how fast we are.
Okay.
And then we'll take the weight lower on the acceleration.
So I think that the reason why the target has not been reached, we can look at the motion again, is that it overshoot. Yeah, there was a bit of a glitch in the viewer. So let me show it again. You can see that it overshoots and then it comes back. So how do we avoid the overshoot? What do we need to?
The velocity.
Yeah, we need to penalize more the velocities.
Or less the acceleration.
I would tend to work with the velocities.
Or
Like experience. It's not enough. Let's try a bit more. 10 to the minus 3. Not enough. 10 to the minus 2. Too much. It doesn't move at all. No, we're not able to reach the target by playing with this. So velocities, let's go back to 10 to the minus 4. Let's try with acceleration. I penalize a bit. No, you were saying penalize less the accelerations, right?
yeah, if you penalize it less, you can do like top of rate.
Yeah, could work. Still overshoots. And indeed, we are not reaching the target. So let me check, just as a sanity check, that if we let it go for longer, we eventually reach it. No. So it overshoots a lot back and forth, and we never reach the target. Let's make it even longer. I want to see how bad it is. Okay, eventually it gets there. Let's see if it printed the message. No. I'm a bit surprised. So let's print this guy here. Error. Yeah.
But you just changed. You increase more the time.
I increased the simulation time,
Okay.
not the MPC horizon.
Okay, the simulation was 100, then
Now it's 500, I think. Yeah, 500. Because it looks that at the end it's getting there. But here it says that the error is still quite large. So it starts with a very large error, which makes sense. And it gets smaller and smaller and smaller. And here we are at the minimum, 0.08, but we are still above the threshold which we set, which was 10 to the minus 2. And then it increases because we overshoot. It increases, and then it decreases, it increases. And then it keeps increasing here. I think this is the overshoot in the other direction. And then it seems to stabilize at a point where we have actually an error. So it seems it's incapable of converging to the target with this cost. That's disappointing. Let's see. Yeah, it's basically converging to this configuration, which is not the desired one. Because you can see that at convergence, we have an error of 0.409. So here we have two options. I'm showing you a bit how I would debug this. I think it's useful. Option one, it's the problem formulation, which is not allowing basically the controller to converge. So it's a matter of tuning the cost, changing the cost. But there is also a second option. What could be the problem?
No, also a related question. I mean, I would say I would raise the position weight, but I think I forgot why we
decreased it. We decreased it because we were getting joint constraint violations. Yeah, I mean, we went from 10 to the power of 2 to 1. We can try something in between, which is 10. Let's see. Not better. No, this doesn't seem to work. So let's go back to the weight of 1. So I think that when you have a problem with a optimization-based stuff, you should always try to distinguish, to understand whether the problem comes from the math or from the computation. Okay, because those are two very different sources of problems. And one way to do that is try to make your solver as powerful as possible, because at least you can get rid of all the possible computation issues. And if you see that even with the most powerful solver out there, you're not able to get a good solution, then probably the issue is in the formulation. So it's in the math. Right now, we don't know, because we are not using the most powerful solver. We are using a solver which has only 3 iterations to converge. So one option would be, let's give the solver, I don't know, 30 iterations, which is not a lot, but maybe it's enough. And let's see what happens.
Is it like real time capable with 30 iterations?
No, not at all. It's just to debug. And yes, so the problem was that the solver had not enough iterations. So if we give the solver more iterations, we reach the target in 56 time steps. So actually, in this case, there is no issue with the mathematical problems that we are defining. So if the solver was able to solve that problem, which it is with 30 iterations, then we would get a good solution, a good behavior of the robots. Very good, actually. No constraint violations, and we reach the targets in 56 time steps. But the problem is that we are only giving the solver 3 iterations, and so, well, it's not good enough. Well, it was good enough before, but then we tried to play a bit with the weights to see if we could achieve still a good performance without the terminal cost and the terminal constraints. And sadly, the answer is no. At least I'm not able to do that. You're more than welcome to give it a try. So just to recap, the configuration that was working was, for instance, the following one. So position weight 100, velocity weight 0, acceleration weight 10 to the minus 6, or maybe it was 10 to the minus 5, but I think it doesn't change much. And then we can add either a terminal cost on the velocities with a weight of 1, or a terminal constraint on the velocities to be 0. And with this setting, even using only 3 iterations, the solver was able to work. So it goes straight there, and we reach the target in only 47 time steps. So this was kind of the best configuration we were able to find. Yeah.
Could you repeat the final configuration?
Well, basically, you have it here. It's 4 numbers. I think it was basically the default one, except that we set this to 1 instead of 0. And another option is, instead of having the terminal cost, to have the terminal constraint, which works, but it's just slower at reaching the target.
Okay. It was the first one.
No, actually, the first thing that we tried was this one. And then we tried to replace the terminal cost with a terminal constraint, which still worked, but slower. And then everything else we tried was either computationally too slow or didn't work. So basically, this is what it looks like to work with an MPC. You set up the problem, and then you start this process, which is a bit trial and error, to work with your ingredients. You have some terminal ingredients, so terminal cost, terminal constraints. You have the cost function weights that you can play with. And at the same time, you have to decide the horizon, you have to decide the maximum number of iterations of the solver, and you have to find a good balance between computational speed and performance of the robot. Another thing that you can play with, which we haven't discussed, is the time step of the MPC. Because of course, if you make the time step bigger, that's going to help in a certain sense, because it just increases the horizon of the problem without increasing the number of time steps. So if I make my time step, I don't know, 20 milliseconds instead of 10, then my 6 steps of horizon are 120 milliseconds and not 60 milliseconds. So I just make my controller look twice as long into the future, or as far into the future. What's the downside of increasing the time step, though?
There's more time between two steps.
Mm-hmm.
So it's like less precise. Could be a collision, like in between two steps.
Yeah, first of all, actually, I would say this is the second point, but since you got it first, the second point is that you only ensure constraints at time steps. So the furthest apart the time steps are, well, the more likely there is constraint violations in between them, which is something that we observed last time when working with the unicycle doing collision avoidance. And then there is a second point.
Less reactive to trajectory changes.
Less?
Reaction to trajectory changes. If I change the trajectory.
Yeah, if you still use the time step as your control period, of course, that's going to make your controller slower, because you're recomputing the control actions every 20 milliseconds instead of every 10 milliseconds. But that's also an advantage, because it means that you have 20 milliseconds of computational budget to do the computation, so you have more time to compute stuff.
It can maybe like it can be numerically not stable.
Yeah, that's true. If you have a kind of unstable system to integrate, having a larger time step can make it more unstable. But even if it's not unstable, like in this case with 20 milliseconds, I don't think it would be unstable. It's just less accurate, the integration. And so basically your prediction of what the robot would do in the future is not going to match well with the reality. So the larger you make the DT, the less accurate you're making your model, basically.
More error.
Yeah, you have more error between your prediction and what really happens, in this case in the simulator, but in reality on the real robot. And how much you can push this to high values really depends on the robot you're working with and on the task you're performing. So again, typically that's decided by trial and error. So what I would suggest you to do is try to simulate the robot with a large time step, and then do the same simulation with a small time step, which gives you like a precise result, and compare them. When the difference starts being large, then you know that the time step you're using is too large and you need to go back.
You repeat why increasing the time step increases the error.
That's a basic principle of numerical integration. So every numerical integration scheme makes some error, and the error is always
increasing the size
of the step. And the error is always proportional to the time step. If you're using a first order method, that's proportional just to dt. If it's a second order method, it's going to be proportional to dt to the power of 2, and so on and so forth. So one way could also be to use a higher order integration scheme, that allows you to use a much larger time step. Runge-Kutta first order, for instance, yeah. But you need to be careful with that, because the time step also decides the discretization grid for the control input and for the constraint. So maybe your integration then becomes very accurate because you're using a high order integration scheme, but then your control input discretization is very poor, and your constraints are only enforced very sparsely. So you might encounter constraint violations in between time steps, like we saw last time for collision avoidance.
I didn't get how the input, if I change the integration scheme, how the input would deteriorate.
No, changing the integration scheme doesn't affect the other stuff, but the idea is that if you change the integration scheme to a high order scheme, like Runge-Kutta 4, that allows you to use a much larger time step. But then having a much larger time step leads to the problems I just mentioned. So sparsity for the constraints enforcement, like collision avoidance or joint position limits.
Because I'm polling the state less and less, the state of the robot.
Yeah. And so also the discretization in time of the control inputs. So now if you make the time step, I don't know, 0.1, then it means that your control inputs are allowed to change only every 0.1 seconds, which is very sparsely. So everything is connected, and you need to be aware of all the connections to be able to tune your controller properly for your application. You had a question?
Yeah, just to recap, I understand, like, we can use the Runge-Kutta, so decreasing the integration error, but still there is the error of like maybe constraint violation that we cannot be able to recover.
Yeah, I mean, you could address that by having additional constraints that consider the state in between time steps, which we mentioned last time. That's not like the classic formulation which we have implemented here, but you could do that. Okay, I think it's a good time for a break. I'll see you back here at 52. Okay, so I think we can stop here for the MPC script because we have played a lot with it. Next, I want to show you another application of optimal control, which is doing minimum time trajectory optimization, which is something that's quite useful in practice. So we can start Jupyter Notebook. And you can go to the folder optimal control, Kazadi Adam. Well, it's the same folder we were in before. And you should find this notebook, which is called minimum time reaching. Okay. Here we go. Before I start with this, just quick information about the next lecture on Monday. On Monday, I want to take you downstairs to the lab to show you a few things that we have going on there. So I'm going to show you an MPC controller running on a robot manipulator and a QP-based controller running on another robot manipulator. So just to show you how these optimization-based controllers can be really implemented on real system, and also to let you interact a bit with them on hardware. So we're gonna meet as usual at 8:30 in the classroom, and then I'm gonna take you downstairs because it's a bit complicated to find the lab. So I think it's easier if I walk you there. So please try to be on time because at 8:30 we meet and we move downstairs. So if you come late, then yeah, you will need to find the lab on your own, which is not easy. So in case you need to find the lab on your own, it's called Mechatronics Lab. And it's at the -2 floor of the Povo 2 building. So you should go to that building, take the elevator down to the -2 floor, and then good luck finding the lab. I mean, you can ask around.
Is the one Formula Star?
Yeah, they are near Formula Psi. Actually, we're gonna be in 2 different labs for the 2 different experiments. So one is the mechatronics lab for the MPC controller, and then we're gonna move to the control system lab, which is on the other side for the experiments with the QP-based controller on the Panda robot. So roughly that's gonna take, I expect, 1 hour. And the second hour, we're gonna come back to the classroom for doing normal teaching. Okay. Now let's talk about minimum time optimal control. We have only half an hour, but I think we can make it. So this is another example of an application that is very often needed for practical purposes because you maybe have a robot manipulator that needs to reach a target and you want the robot to reach that target in minimum time. Or you have a mobile robot like a unicycle, and again, you want to reach a certain location in the environment and you care about reaching it in minimum time. And so far, we haven't seen how to do that. And that's not really trivial because if you look at the standard formulation of an optimal control problem, this is in discrete time, there is no way to say, I want to minimize the time for reaching the target. Because the cost function needs to be a function of the state and the control. The horizon is fixed, is given by the number of time steps, capital N, and the duration of the time step, dt, which are fixed. They are not optimized. And so it's pretty hard to say, well, how do I achieve a trajectory in minimum time? Do you have any idea for how to do that?
I'm not sure what usually it's a bang-bang controller.
So the result of a minimum time optimal control problem is going to be a bang-bang control. But how do you get it with an optimization solver?
Editorial function.
Hmm?
The editorial function, editorials are called the optimization.
Good luck with that. Yeah, I mean, in some specific cases, there are like analytical or semi-analytical solutions to this problem. But if you want to tackle in the general case where you can have like any inequality constraint for modeling like joint position limits, joint velocity limits, joint torque limits, obstacles in the environment, then those methods don't apply.
You just write like the time t and like into your optimization problem, and then you optimize just over the time because it's like basically the only constraint you're giving 1 minute.
But t does not appear here.
Yes.
So you would mean n,
Yes.
capital N.
In this case.
Okay, so you're saying, well, I just want to optimize capital N to be as small as possible.
If you don't care about it.
N is an integer variable. And like standard gradient-based solvers can only work with continuous variables. Because then if you have an integer variables, gradients don't really apply.
Either that. Yeah. Could I find some method to maximize velocity?
So instead of saying minimize time, say maximize velocity. I could go very fast, but still reach the targets taking a lot of time. Like if instead of going straight to the target, I go very fast in that direction and then I come back very fast. I have maximum velocity maybe, but I've reached the target in a lot of time. So it's not necessarily what we are looking for.
Minimize distance, so trajectory.
Yeah, so one option, which I think is most intuitive one, is to use the running cost to minimize the distance to the target. And intuitively, that's going to push the solver to find a trajectory that gets close to the target as soon as possible. So that's probably something that we have also encountered at a certain point during our lab sessions. Well, it's actually very close to what we were doing a moment ago in MPC. We had a term in the cost function that was penalizing the distance to the target configuration, and that was pushing the controller to reach the targets very fast. But this is not really minimum time. This is like an approximation of minimum time. And there are a few potential issues doing that. So one issue is how you define the distance to the target. So the typical approach would be to use the L2 norm, like the square of the distance. And the problem of that approach is that the gradient of the L2 norm goes to 0 as the argument of the norm goes to 0, because it's a quadratic. And the gradient of a quadratic is linear. And so when you go close to 0, also the gradient gets close to 0, which means that typically the solver would be happy before reaching 0. Because when the gradient is sufficiently small, then since you typically have also other terms in the cost function for like minimizing accelerations or minimizing, well, not velocities, maybe not, but accelerations, it's always a good idea, because that gives you a bit of regularization to the problem. So it would typically be happy when it's sufficiently close to the target and it doesn't really reach the target. And to overcome that issue, you could switch to the L1 norm, which doesn't have this issue of having a gradient that goes to 0 as the argument goes to 0. But with the L1 norm, you have a different problem, which is non-differentiable at 0, because it's like the absolute value. So it's linear here, but at 0, it's non-differentiable, because the derivative on the right side is 1, and the derivative on the left side is -1. So you don't have a derivative at 0, which means that the solver doesn't like it. So it's going to take it. It's not going to complain if you use the Casadi, but the behavior could be not very good in practice. So typically when you want to use the L1 norm, you try to introduce some regularization so that when you're close to 0, you get like a quadratic behavior instead of a linear behavior. And in that way, it's differentiable everywhere and the solver behaves a bit nicer. But these are all like compromises. So you're always gonna have like an approximate minimum time solution. If you really want a minimum time solution, you need to do something different. Any idea? Let's go back to the standard problem formulation. So the horizon length depends on 2 parameters. The first one is capital N, the number of time steps. But that's an integer, and so we cannot optimize it. What's the second parameter? The time step. And is a time step an integer? No, it's continuous. So what about we optimize the time step? We can say that the time step, we call it h, is a decision variable of the problem. So we add it to the list of decision variables. We minimize it in the cost function. So we add a term to minimize the time step with a given weight. And then the dynamics is going to be computed using the time step h. So here FC would be the continuous time dynamics. And here I just implemented a very basic Euler integration scheme. And then you may want to have like a lower and an upper bound on the time step. So you don't want the solver to make it too large or too small. Especially you don't want the time step to go below 0. So for sure a lower bound I think is a good idea.
And how we can dynamically set dt. I mean, isn't dt a parameter of a controller?
Here we're not doing control. Here we are doing trajectory optimization. So now we're not in an MPC setting. We are doing trajectory optimization, and then typically what you would do is that you first optimize the trajectory that is minimum time, and then you take this trajectory as your reference, and you might use an MPC controller for tracking it. And then in the MPC controller, the time step would be fixed. But here you could make it variable. And basically that's it. That's the idea. Makes the time step a decision variable of the problem. So with this, you're really minimizing time. Yeah.
You have some, I don't know what I'm asking here, but okay, you have to like know the states kind of before, like and the controls, because you have to fix those before solving the time step.
No, you typically only know the initial state,
yeah,
and the desired terminal state, or the terminal like position of the end effector. Maybe it's not the complete state that you know, just where the end effector should be. And that's it.
So the states are unknown and the time step is unknown?
Yeah, everything is unknown. Everything is discovered automatically by the solver.
And it's that's solved numerically, right?
Everything is solved numerically, yeah. What are the potential issues of doing this? There's one issue.
Too high time step. No, because it's bounded, so
it's bounded, so it cannot go too large, and also it's minimized in the cost function, so it shouldn't go too large. But it's related to that. So
also like before, so the integration step. I mean, like before, if we have a big time step, we have could be a issue or constraint inside this time step. So the accuracy is going to be depending on how much how big is the time step.
The problem is exactly what you described. Is basically that the accuracy of our integration scheme of our constraint enforcement is going to depend on the solution that the solver finds. So we don't have a fixed accuracy, and then the solver finds a solution, but now accuracy and the solution, they are coupled. And so depending on how we set up the problem, we may end up with a value of h, which is so large that the integration errors are very significant. And also the constraints, they are enforced too sparsely. And so you might have violations in between constraints. And you don't know that until after you have solved the problem. So maybe it's going to require a bit of back and forth for, like, for instance, figuring out how long the horizon should be in terms of number of time steps. So for instance, you could try, I don't know, to set capital N to 100. You solve the problem. And then if the value of h that the solver finds is too large for the accuracy you would like to achieve, then what you would do? So suppose you set capital N to 100, you solve the problem, and the solution found by the solver has a value of h, which is too large, like it's 50 milliseconds. And we know that 50 milliseconds is too large because then the integrator is not accurate. What would you do then?
Increase n.
Increase n. You increase n, because if you increase n, that's gonna decrease h.
But then the computation time is going to be.
Computation time is going to be larger, but this is something that you solve offline. It's not an MPC, so you don't care too much about it.
You could also decrease h max. If you allow h max to be 15.
Yeah, but if the solver has found a solution here that is 50 milliseconds, and that's a solution that minimizes h, and you set h max to be smaller than that, you made the problem unfeasible. So you didn't solve the issue. So your main knob for improving that is capital N. You need to find a value of capital N that is sufficiently large so that h can be sufficiently small. Because the horizon is basically the product of these two values. So if you want to make one small, you need to make the other one larger. Okay, so now we just go through the setup of the problem. We are doing it for a robot manipulator. So we have the usual model of the robot dynamics with the acceleration set as control inputs and the joint torques computed using the inverse dynamics of the robot for setting the joint torque bounds. We have already seen that. Usual imports, robot model. These are the parameters. So we are defining the minimum time step to be 1 millisecond and the maximum one to be 100 milliseconds. The number of time steps, I set it to 150. And we want to reach this position with the end effector. So the target is only in the end effector space, not in joint space. The joint space configuration is free. And at this moment, I only have a cost on time. I don't have any cost on velocities nor accelerations. So here I define the dynamics of the robots, which is just a double integrator. Here I define the inverse dynamics. This is all stuff we have already seen. Forward kinematics for computing the end effector position. Here I'm getting the joint limits from the model, and I'm printing them just for your reference. The maximum velocities are about 3. The maximum torques are 150 for the first 3 joints and 28 for the second 3 joints. Here I create my decision variables, which are the usual state and control trajectories, but the difference is that here I'm adding one extra variable, which is the time step. So dt is an optimization variable of size 1, and it is bounded between dt min and dt max, as I said before. Here I define the optimal control problem, which has the usual torque limit, dynamics. So the dynamics is computed using dt, which is a variable. And here I have some costs on the velocities and the accelerations, but actually they are set to 0. One thing to remember, dt should also scale the running cost. Because now, I mean, when typically dt is fixed, we don't need to have dt in the running cost. But now that dt is a variable, I need to account for it even in the running cost. Because I'm like integrating a continuous time function using like an Euler approximation. So when I switch to discrete time, the integral should contain the dt over which I'm integrating. If the dt is fixed, of course, there's just a constant multiplication of the cost by a constant value. So it doesn't affect the optimum. But in this case, since this value dt is not constant, it needs to appear in the cost function integral. I set the terminal state to be equal to the desired end effector configuration with 0 velocities, and I set a cost on the time. Here I create my solver as usual, and here I solve the problem. So the solution found was to set the time step to 4.1 milliseconds. And so the total horizon is 0.6 seconds. So that's the time it takes to the robot to reach the target. And here I just have the viewer set up. And this is the viewer with the robot. So the red ball, as usual, represents the target state. And this is the minimum time motion that has been computed. That's it. Now we can do some plots. It's better to go here to see the plots. So this is a plot of the end effector trajectory. Well, nothing special to see there. We can just see that it reaches the target. It's more interesting to look at the joint velocities because we can see that they very quickly saturate to their maximum value, which was around 3. So some saturate to the maximum positive value, some to the minimum value, but there is a saturation of 3 of them, which makes sense. That's what you would expect from a minimum time trajectory, that it saturates the velocities and the torques. That's a bang-bang behavior you were mentioning before. And here is instead what happens to the joint torques. And we can see there is a saturation here at minus 150. And there is a saturation at the end at plus 150. So roughly we can see that the motion has 3 phases. There is an initial phase which is of maximum acceleration where we saturate the joint torques of several joints. Then there is a maximum velocity phase where we move at maximum velocity. And then there is a final phase, which is a maximum deceleration phase where we decelerate with maximum torques again. And that's a classical structure of minimum time motion. You have saturation of the joint torques at the beginning and at the end, and saturation of the joint velocities in the middle. That's it.
On the last one.
This one.
Yeah, the one that was following -3, around -3.
Yeah.
That was where you described where you maximize the what? What was it again? I didn't catch what you were saying.
So there is the first phase, which we see very well here, which is of maximum joint torques. So we saturate the joint torques because we try to accelerate as fast as possible to reach the targets fast. And then here, a bit before 0.1 seconds, we reach the maximum joint velocities. And so we can no longer accelerate. And so we remain at maximum velocity. And so the joint torques go from the bound to an intermediate value, which is the one that it's needed to stay at constant maximum velocity. And then at the end, we have the opposite happening. We want to decelerate as fast as possible. And so again, we saturate the joint torques, but in the other direction. Yeah.
Are we happy with this full saturation of the torques?
Well, that's exactly what we are asking for. So if you want a minimum time motion, you're going to saturate your actuators, period. There's no other way. So if you don't want a truly minimum time motion, then no problem. We can do that. We just have to add some penalties, for instance, on the accelerations. I don't know, we add a penalty of 10 to the -5. We rerun everything. By the way, a minimum time problem is quite hard for the solver. So it takes some time to solve it. And now we can see that we went from 4.something to 5.6 as a time step. So it's no longer minimum time. It took it longer. But probably we're going to have like smoother trajectories. These are the velocities. Now they're much smoother, you can see. And now the torques are not saturating anymore. So by tuning that weight, you can achieve a trade-off between these two extremes.
Could we make it faster by like doing a variable time step length?
So you could specify a different time step for every time step.
Yes. I think that right now we're having a fixed one for all.
Yeah, we have a fixed time steps for the whole horizon.
Yes.
I think, yeah, you can do that, definitely. I don't think it's a good idea because exactly of this issue here, which I mentioned. That the solver may exploit integration errors to artificially decrease the cost. And I think that's much more of an issue if you have an independent time step duration for every time step. Because then the solver could make certain time step very small while others are very large.
Yes.
And that means that at certain time steps, you have a very small integration error, and at others, you have a very large integration error. And this leads to like artifacts in the trajectory. And I think in general, you don't want that. So I think it's better to fix the time steps for the whole horizon to be the same. So at least the integration error is uniformly distributed along the trajectory. That gives less room to the solver to exploit integration error to minimize the cost, which is what the solver tries to do always. Okay, well, you have the notebook. You can play a bit with it, but yeah, in general, I would say that this trajectory, the first one that we got, is satisfying because we have a small time step which is a bit higher than 4 milliseconds, so it's typically good for a manipulator, and the trajectory looks good. You can try to change the target, to change the weights, to change the number of time steps to see what you get. It's a very useful application, I think, for practical use cases. So we can stop here because we don't have time. And I'll see you on Monday at 8:30 in the usual classroom. Please try not to be late because, well, we're going to leave like at 35. See you on Monday.